Hi everyone, it's my great pleasure to be speaking at a summer school in Seoul National University, my alma mater. And today I'm going to talk about how we can make our natural language understanding systems more realistic so that we can use them in the real world scenarios. So we will talk about natural language understanding and what it is. So there could be a lot of different definitions, but I would like to quote Bender and Kohler that says, NLU is a grand challenge of artificial intelligence, which involves mastery of the structure and use of language and the ability to ground it in the world. So natural language understanding is an area in the intersection between academic research, where we care about fundamental and foundational approaches for computational machine intelligence, as well as real-world applications where we care about deployable systems that can assist humans in real life, like search engines, personal systems, and fact-checking systems. So in the past, the problem of NLU has been studied by identifying sub-problems in NLU and designing systems for each of them. And such sub-problems include syntactic parsing, named entity recognition, co-reference resolution, and semantic parsing. More recently, in the era of deep learning, the problem of NLU has largely been reshaped. And people have found promising to annotate large-scale data sets or tasks designed to test NLU and train the neural model. So such effort led to benchmark data sets like GLUE and SuperGLUE that consider linguistic diversity, as well as SQUAD, a question answering benchmark where annotators write a series of questions to test the machine's understanding of the given passage. And as you may already know, there has been rapid progress in NLU thanks to the advances of deep neural network, data available on the internet, and strong computational power coming from advanced hardware systems. And such effort made a big progress in NLU. For example, we achieved superhuman performance on a SQUAD dataset. And there is GPT-3, which achieved impressive performance on SuperGLUE benchmark only with a few training examples. And what you can notice here is that all of them are evaluated on benchmark tasks like GLUE and SuperGLUE, so they are not same as real-world tasks. So it's time to ask a question, are we climbing the right hill? And in today's talk, I will argue that there is a big distinction between benchmark tasks and real-world tasks. Benchmark tasks are simplified tasks with many assumptions to make evaluation easier. On the other hand, real-world tasks are real problems as they are, so we cannot really make assumptions as we want. So in this talk, I will argue that we really need to relax such assumptions that are inherently false in the real world. And there could be a lot of such assumptions, but I would like to identify 3 of them that I think are the most inherent and need a fundamentally different ways to think about our problem. So the first assumption I'd like to mention is the assumption of perfect background knowledge being given to the model. For example, in a benchmark task, we assume a single passage that contains perfect background knowledge to solve the problem. Like here, the passage contains answer to the question. However, in the real world scenario, we do not really have this passage. When you ask a question to a machine, the question that you ask is the only input to the machine, and the machine should find the background knowledge itself. And it turns out that the state-of-the-art model in 2019 suffers from this problem, even with BERT, achieving accuracy of 26. So we can learn here that we need a model that can find background knowledge itself, potentially from external sources. And the second assumption I would like to mention is the assumption of well-defined input from users, which almost all NLU research so far has been assuming. And this is perhaps obvious because to train the model, you need a large set of well-defined input and output pairs. However, we know that this is not really true in the real world because users often do not know how to formulate the input so that they can find what they want from the machine. For example, we look at the real user questions that appear to be unambiguous, and found that over 50% of them are in fact ambiguous, not having a single definite answer. Also, we found over 30% of questions from Reddit are invalid because they are based on false presuppositions. So these problems are inherent. However, current tasks do not consider this and rather treat them as noise, which is not a principal way to tackle this problem. So we argue here that we need a new task formulation that can embrace inherent ambiguity and false presupposition that could naturally occur during information gathering. So let's say we have great model, great task. What about the learning method? Are we all satisfied with the current learning paradigm? Well, we already know that we have been focusing on a very narrow definition of learning, where when we have n different tasks, we collect n different data sets and train n different models. And this is not really feasible in the real world. First, because we cannot really collect large-scale data sets for every possible task. And second, each of these models is getting larger and larger. So training and saving the entire model parameters for every possible task is not really possible. So we argue here that we need a better training paradigm for achieving two goals: better data efficiency and parameter sharing. So this is the overview of today's talk. So in the first part of the talk, I will present the knowledge retrieval system that can retrieve knowledge and process them from external sources like Wikipedia. And in the second part, I will show how we relax the assumptions of well-defined user input by embracing potential ambiguity in user questions. And finally, I will present a new training paradigm called model prompting that achieves two goals that I mentioned: data efficiency and model sharing. And finally, I will talk about the conclusion by giving a summary and present avenues for future work. I see the messages about the sound. Does it sound better now, or do I need to adjust it? There we go. So now I will start from part one, knowledge retrieval. So let's talk about the problem set first. So let's say you have a user question like, who is the bad guy in Harry Potter? And you have Wikipedia that is very large. It contains 21 million passages. And what you're gonna do is you have a model that receives a question and Wikipedia as an input and output a small subset of Wikipedia passages, say 5 to 100. And the idea here is that this subset of Wikipedia passages should support the answer to the question. So once you get these passages, you can fit them to another model that reads these passages and generate the answer to the question. And this problem is very challenging for two reasons. First, the retrieved passages should contain and support the answer to the question, which is typically 1 or 2 out of 21 million. So this is a very hard problem even for humans. The second problem is that the model should efficiently operate over millions or billions of passages. For example, you should return the output of the model in 1 second or more than 0.5 seconds. And perhaps surprisingly, the state-of-the-art method since until 2019 has been a non-neural model, so-called lexical matching, including TF-RF and BM25. And the key idea here is that you count all the words appearing in the question and passages and see how much overlap there is relative to the overall frequency of the entire corpus. And this looks very nice, very simple, but it is actually a strong baseline on annotated benchmark like SWOT. However, we know that this is limited for real user questions like information-seeking questions, because this method does not really consider the semantics of every word. So it achieves only an accuracy of 26 on such a data set. So at this point, I will present our work that was presented at EMNLP 2020 called dense passage retrieval. And this is one of the first work that shows that in the domain of question answering, neural models can significantly outperform lexical matching baseline without expensive data and compute. So the idea is pretty straightforward. We have a neural retrieval model based on a dual encoder, which is often called dense retrieval. And we have two encoders, one for passage and the other for question. And we map the question and passage into h-dimensional vectors. And we compute a similarity score between the question and passage using an inner product between these vectors. And what will happen at inference time is that you map all the passages from Wikipedia to the dense vector space. And then once you have a question, you map the question into the same vector space and take the nearest passage vectors as the output of the retrieval system. So I must mention that we are not the first that studied this idea, and it has been studied in the literature for more than decades, also known as Siamese network. However, it was actually not trivial to make it better than lexical matching baseline. In fact, to train this model, you need a large amount of label data, for example, nearly 100 million training examples. And this is not really easy to collect such a large data set. More recently, there has been work from Google that showed that it is possible to do some retrieval-specific pre-training and outperform lexical matching baseline. However, this pre-training method is very expensive and is still unstable to train end-to-end. So we can safely say here that we show for the first time that we can build a state-of-the-art neural retrieval model for question answering without significant amount of label data and computation. So I will deep dive into the methodology. So we have two encoders, each based on transformer model initialized from BERT embeddings. And then we map the question and passage into h-dimensional vectors using these encoders. And then we compute a similarity score by using an inner product. So to train the model, you need a training data that consists of a question, a positive passage, and n-1 negative passages. And here, a positive passage means passage that contains any support the answer. So basically the passage that we want to retrieve. And negative passages mean those that are not really what we want. And we can train this model using a negative log likelihood objective, where we are maximizing the inner product between the question and positive passage against negative passages. So it is pretty straightforward, but it turns out that it still does not work. So we had to come up with two core ideas to make it work. And the first idea is to carefully choose negatives to train the model, so-called hard negatives. And the idea here is that negatives should be those that the model is likely to be actually confused with. So let's take an example. Let's say we have a question, who is the bad guy in Harry Potter? And here is a corresponding Wikipedia passages that contains and support the answer. So now let's say we have random negatives uniformly sampled from Wikipedia. And such passages are likely to be not really related to Harry Potter because we uniformly sampled. So you can see passages about New York, about Beatles, or Summer Olympics. And it's pretty likely that a reasonable retrieval model would obviously know that these passages are not really related to the question because it doesn't really overlap in context, which means that the model doesn't learn much from these random negatives. So what if we choose a set of hard negatives, which are somewhat related to the topic of the question, but is not really supporting what the question is asking about? And such passages are likely to be about other characters in Harry Potter or villain characters in other movies. And it turns out that using hard negative is much better than random negative. So that was the key idea to make DPR work. The second idea I will present is a new objective called in-batch negative training. And here is the idea. Let's say we are training on a batch of data consisting of B questions. And each question has one positive and n-1 negatives. What we do with vanilla training method is that each question is paired with n-1 negative, so it receives n-1 signals. What we do with in-batch negative training is that we use passages paired with other questions in the same batch as additional negatives. So each question will receive bn-1 negatives corresponding to BM-1 signals. So the key idea here is that in-batch negative training increases the number of effective negatives, so that it increases the number of effective signals. So this having more negatives is the key to make dual encoder work. So I will move on to the result where I'm presenting the recall accuracy of the model. Here are the results of BM25, which is the state-of-the-art lexical matching method. Here are the results from DPR, and we could see that DPR significantly outperformed BM25 over all datasets. We also experiment with DPR multi, which is DPR trained on a combination of QA datasets. And we see additional gains, especially on small datasets like thread. And here are results of the end question answering accuracy. And we see that DPR again set the new state of the art. In particular, the yellow bars are from the previous work that used very expensive retrieval-specific pre-training, but DPR outperforms all of them. So that means that it is possible to build a state-of-the-art retrieval model even without this expensive computation. So we have a web demo where you can visit and type your own question and see how well the model does. So please visit the website and play around with this. It should be quite fun to try it out. So since we published DPR, we were very excited to see that the community has found it impactful. And there has been a lot of follow-up work during a year. So some work studied DPR for tasks beyond trade. The other work extend DPR for question retrieval, use DPR for retrieving heterogeneous knowledge sources, and use DPR for multilingual question answering, which are all very exciting. In fact, in last year, in 2020, the researchers in the community, including myself, were very curious to see how much we can push toward even better QA system. So we organized a New Year's competition called Efficient QA. And this competition focuses on information-seeking question answering with additional focus on memory constraint. The competition was quite successful, receiving 39 submissions from 18 unit teams within 2 months. And participants made significant progress, advancing the state-of-the-art by a large margin. And I was personally more excited about it because all the top 8 submissions made use of DPR. And here is the top 1 submissions from Facebook AI that extended DPR. So just like DPR, they started by mapping knowledge sources to the dense vector space, but not only the passages from Wikipedia, but also tables from Wikipedia and triples from structured knowledge graphs like Wikidata. So the retrieval system can retrieve a combination of these heterogeneous knowledge sources. And then these are fed into another model called Fusion Encoder, which can reason over the sources and generate the answer. And here are the results of the competition, where I'm showing the result of the Microsoft system that won the 2nd place and the Facebook system that won the 1st place. And here are the results of DPR, which are their starting point. Here are the results of their own system, and we could see that they achieved impressive gains over DPR, which is very exciting. However, we find that actually automatic evaluation significantly underestimate the model performance. So we did a human evaluation and then find that the model achieved near 70. And then finally, we filter out ambiguous questions and evaluate on unambiguous questions only. And the best performing system achieved an accuracy of 83%. And this is very amazing, given that these advances happened in like 1 year. So far, I have been mainly talking about a question answering task because it is a representative task for NLU. But the same modeling ideas has been successfully applied to a larger body of other tasks. So DPR has been extended to tasks like slot filling, dialogue, fact-checking, entity linking, and generation. So we were very excited to see this progress. And then so far, I've been mainly talking about a few things about DPR, but obviously there are limitations that are avenues for future work. And there could be many of such limitations, but I will mention two of them. So the first limitation is that dual encoder models are known to have a significant problem in suffering from out-of-domain distribution. And perhaps this happens for every neural model, but actually dual encoder turns out to have it more significantly than other types of models. And I think this is really important problem because annotating retrieval data set is very hard. So we cannot really annotate data set for every possible domain. So we should develop a model that can generalize better. The second limitation I want to mention is how to train this model for abstractive generation. And the problem is that training the DPR relies on positives and negatives. However, obtaining these data sets are not really trivial for abstractive generation. So you can imagine something like how questions or why questions where the answer is not a short text. So I think it is a really important problem, and if we could make it without positives and negatives, it will be highly impactful. Yeah, so far that was part one, and at this point I can take some questions if you have any. Okay, so if we don't have questions, maybe we can move on to part two, where we will talk about how we relax the assumptions of well-defined user from well-defined user input. And we do this by embracing potential ambiguity of user questions. So why is this an important problem? So let's take an example. Has anyone watched the TV shows called Grey's Anatomy? Well, it's a popular TV show in the US, and there are two main characters, Meredith and Derek. They are married, and a reasonable user can ask a question like, what season do Meredith and Derek get married in Grey's Anatomy? And what do you think about this question? Does this question look ambiguous to you? Well, it didn't look ambiguous to me when I saw this question, but when I read Wikipedia text carefully, I realized that this question is ambiguous. And this is because Meredith and Derek got informally married in season 5, and then got legally married in season 7. And this ambiguity is so subtle, being not apparent before reading Wikipedia text carefully. And then it's an inherent problem because if you do not have the full background knowledge about this marriage, you really do not know like whether this is ambiguous or not. So there is no single definite answer to this ambiguous question. So what we found is that actually more than 50% of user questions that appear to be unambiguous by the question alone are in fact ambiguous. And such ambiguity was very subtle, just like the example we saw. And what we want to highlight here is that this is an inherent problem because users fundamentally do not know how to formulate the unambiguous questions when they do not have full background context and when they're gathering for new information about topics they're unfamiliar with. And if you imagine, if you have the full context, you will not really need to ask a question. So this means that real user questions are inherently ambiguous. And before moving on to details, I must mention that although it is an inherent problem, it is a hidden problem. So previous work in QA has been assuming a single clear answer to every question, partially because it looks unambiguous. However, people observe that even very high quality answer annotation often have very low agreement rate. For example, on the NQ dataset, which is known to have very high quality annotation, the answer annotation agreement rate is actually not more than 50%. And this is really unintuitive, and people were having a hard time understanding why this is happening, and just treat it as sort of noise. However, we argue here that we need to embrace ambiguity as a natural problem of real user questions like information seeking questions, and maybe propose a task that can solve this problem in a more principled way. And another body of work has been studying ambiguity. But the problem is that they have been looking at intentional ambiguity rather than natural ambiguity. For example, they hire crowd workers to annotate intentionally ambiguous questions. And it turns out that such ambiguous questions are actually so obvious. For example, you have a question like, what is the job of Michael Jordan? And it's relatively obvious that there is ambiguity in the person name. And obviously, you have a long list of people named Michael Jordan. And then we should say that we want to study different problem, which is to look at natural ambiguity. And this is more subtle and more challenging to identify. Okay, so I will present our work that was presented in EMNLP 2020 called Ambiguity. And this is a new task formulation to tackle this problem. And the goal here is that the system must identify all equally valid answers to the question and disambiguate them. So more specifically, this is how it works. A system is given a question and is supposed to output a set of question-answer pairs where each of them contains an equally valid answer to the question and disambiguated question that is minimally edited from the original question to differentiate these two answers. So for example, in the question, what season do Meredith and Derek get married in Grey's Anatomy? The system must identify both season 5 and season 7 as the equally valid answers. And then they should add keywords like informally and legally to each question to differentiate informal marriage and legal marriage. So in this way, the system can still explicitly answer to the original question while additionally providing disambiguation in a more concrete way. So as we just defined the task, we need to collect data to train the model. And this was actually the hardest part of the project. And this is because the task is even difficult for humans. Especially maximizing recall is hard because the ambiguity is not easily found before reading Wikipedia text carefully. Nonetheless, we were able to collect high-quality data with high levels of ambiguity using careful vertical selection and annotation pipeline consisting of generation and validation. So here is how it works. We first take an information-seeking question from real user from the NQ dataset. And then we give this question to two generators where they independently annotate the data, like giving answers and disambiguations. And finally, a validator is given these generations and validate them by either choosing one of them or taking a union. So the key idea here is that annotation from a single generator may not be enough because it is easy to miss some plausible answers. However, by having two independent generators, we could expect that at least one of them will find the answer that the other might have missed, which could be later validated by a validator. So the agreement in generation is 61, which is relatively low, but the validation agreement is near 90, indicating the high quality of the data. So in total, we have 13K questions for ambiguity, and over 50% of questions are ambiguous. And this is actually a surprising ratio, given that NQ has been a popular benchmark to output a single answer. And here is the table for types of ambiguity, including event references, properties, entity references, and so on. We could see that they are fairly diverse, indicating that modeling of a single aspect will not be enough to solve the task. And here is the word cloud of the edits made in the questions, and we can see they are fairly diverse. And if you're interested in, there are more analysis in the paper, so please take a look. Now we have collected the data set, so now it's time to build the baseline models. We experimented with 3 different baselines. The first baseline is the most naive method that is called disambig first. So this method runs disambiguation first before reading Wikipedia, and then answer to each disambiguated question. So what you could see is if the ambiguity of the data is not trivial, these models should not work well, because disambiguations cannot be really done by the question alone. The second baseline is called DPR plus reader, where we use the state-of-the-art QA model, DPR, to find multiple answers and then disambiguate them. And DPR is designed to output a single answer, so we had to do some thresholding over likelihood to allow it to output multiple answers. And the limitation here is that outputting each answer is done independently, so it cannot really consider a set of answers jointly. Therefore, we consider the third baseline called span-seq-gen, and this used DPR as its first component, but then use sequence-to-sequence model to jointly generate a sequence of answers, like season 5, special token, and then season 7. So you can potentially jointly consider a set of answers. And the additional method that we considered as our sort of contribution is to use code training algorithm to use weak supervision. So the idea here is that given prevalence of unlabeled ambiguity in NQ, which is a much larger data set, we can make use of a known answer annotated in NQ as weak supervision to train the ambiguity model. So here is how it works. We first train C sequence-to-sequence QA models using ambiguity data. And then we give the question from NQ to the model at inference time, but using NQ annotated answer as prefix, so that each model will generate more answers or finish generation if it thinks it's all. And if there are answers generated by a majority of the model, we can use them as an expanded version of our data. And we can use them to retrain C sequence-to-sequence QA models. And this process could be done iteratively. Now I will move on to results. So first, these are the results of this ambig first, our most naive baseline. And we could see that they perform relatively poorly, indicating that ambiguity is indeed non-trivial, being not found before reading Wikipedia. And this is the result of the second baseline DPR, and we could see that finding answers first and then run disambiguation works. And this is our main model, span-seq-gen, and we could see that it outperforms the other two baselines, indicating that jointly modeling a set of answers works better. Finally, we see code training can further boost the performance, indicating the potential of using code training algorithms to use weak supervision. So we made a website where you can navigate the data and see the leaderboard for the most up-to-date model. So please take a look. And we are very excited to see the progress from the community already. So I highly recommend to take a look. And since Ambiguity was published, there has been a lot of follow-up work already. So there has been work that proposed better ambiguity models, like the state-of-the-art models I mentioned, studying ambiguity as a failure of the presuppositions, studying ambiguity beyond QA, studying geographical and temporal ambiguity that Unso mentioned earlier today, and studying ambiguity with respect to the data bias, and then retrieval for all valid answers, which is actually my own work. And I think this is a really interesting and important topic, but it is also relatively underexplored. So I think there is a lot of work to be done. So I hope you find it exciting too. Yeah, this is the end of part 2. And in the meantime, do we have any questions? Yeah, if there is no question, maybe I can move on to the last part where, oh, do we have a question? So we have a question says, 집단 지성을 어떻게 생각하시나요? I'm not sure what you exactly mean. Are you thinking of something like ensemble model, or I mean like a collection of people or a collection of systems? I'm not entirely sure if I understood your question, but if you mean like if we can improve collection of if we can improve NLP system using a collection of people, I think yes. And actually, all of the advances that use crowdsourcing data set is actually using a collection of people. Like a lot of people are annotating data set and we are training the model. So I think we are already doing that. There could be more diverse ways of using this. Like maybe you can use sort of interaction as we saw from the previous talks. So there could be many ways to do that. Okay, so I will move on to the last part now, where so last part where I will talk about a new training paradigm called model prompting. So it's like a transition from realistic task to realistic methodology that can be applied to any kind of task. Okay, so here is the problem. Suppose you have n different tasks. You have to collect n different data sets and train n different models. However, an idle NLU system should be able to do very well on a wider range of tasks without task-specific parameters or with very limited number of task-specific parameters. And ideally, such a system should be able to learn from a handful of training examples so that we don't really need to use a large-scale data set. And this is a setup often called few-shot learning. And there has been a lot of work for this problem, but today I'm gonna talk about a new training paradigm called prompt-based learning. And this is a new way of using a large pre-trained language model for a downstream task we care about. So for those who are not familiar with language model, here is what it does. So a language model can take a sentence or a list of words as an input and calculate the conditional probability of the next token or next sentence. So for example, the system can receive an input like Python is a multi-paradigm programming language, and it can compute the conditional probability of another sentence like Python is one of the most popular programming languages following the input sentence as. And this value is likely to be relatively high because these two sentences are relatively relevant in context. You can also calculate the conditional probability of another sentence, like English is the third most spoken native language. And this value is likely to be smaller than the first one because these two sentences are less relevant in context. And it has been well known that if you pre-train the large transformer model using a language modeling objective and then fine-tune the model on a downstream task we care about, that has been a de facto method in NLP. So prompt-based learning is actually an alternative way to use language model for the downstream task. And it can replace fine-tuning at all. We use language model as it is without updating any parameters. So here is how it works. Suppose you're interested in a topic classification task where you're given an input like why are Boolean values capitalized in Python? And then you must classify the topic of this sentence to one of the topic candidates here. And what we're going to do is you feed this input sentence to the language model as an input as it is and compute the conditional likelihood of the sentence like it is about computer and internet. And the idea here is that this square is likely to represent how likely it is that the input is about the topic, computer, and internet. And you can calculate this for all other classes like society and culture, and then you can compare these values to see which class gives the largest value. And if the value for it is about computer and internet gives the largest value, you can classify the sentence to the class computer and internet. So that's how you can use this language model. And you can go even further. For example, you can feed a number of tokens, number of vectors to the language model as an input and learn these vectors for the downstream task we care about. And these vectors are called prompts because these vectors are learned to prompt the language model to do what you want, which is to perform well on the downstream task. And apparently, this prompt-based learning is much more efficient than fine-tuning because fine-tuning requires to update the model parameters that is typically millions or billions or even trillions. But in the prompt-based learning, you learn only a few vectors that consist of a few thousand parameters. So it's much more cheaper. So people have found it promising, but there has been a lot of identified problems. And one of them is that prompt-based learnings are very unstable, having high variance across different verbalizers and seeds. And the worst case accuracy is often not really better than the random guessing baseline. So the question here is, how do we tackle this problem? And in our very recent preprint, we proposed a new method that uses noisy channel approach for language model prompting. And the idea is pretty straightforward. Yeah, I see the question about DPR. Maybe I'll answer this after this section. Yeah, so the idea is pretty straightforward. So let's say the X is the input sentence, like why are Boolean values capitalized in Python? And Y is the output sentence, like it is about computer and internet. And what the models we have been seeing so far does is you calculate the likelihood of Y given X, and we call them direct models. What noisy channel model does is to reparameterize Py given X to Px given Ypy divided by Px using Bayes' rule. And then this is proportional to Px given Ypy. We don't really have to care about Px because this is independent from the class value. And that's what noisy channel model does. The channel model computes Px given Ypy. And if you care about classification task, you can assume uniform distribution over labels. So you can essentially compute Px given Y. So what you could do is you feed the output sentence, like it is about computer and internet, to the input to the language model, and then calculate the conditional probability of the original input sentence, like why are Boolean values capitalized in Python. So this looks pretty simple, but noisy channel model is actually based on solid foundations and has been a widely studied topic in machine translation and has been extended to other tasks. And there has been theoretical analysis that say channel models learn from data more rapidly than their direct counterparts, which is useful for the few shot setup. There has been a lot of work that show empirical results that channel models are more robust to a distribution shift and works better in a few shot setup. So our work is really in the same line of work, but we are proposing to use this noisy channel model for language model prompting. So now I will deep dive into the methodology. We have 3 different methods, and the first one is our main method called prompt tuning. And as I said earlier, this is to prepend the prompt vectors as the input to the language model and tune these vectors while freezing all other parameters. And the other 2 methods are sort of stronger direct baselines. The first baseline is head tuning, where we are tuning the head, the upper layer of language model only, and then freeze all other parameters. And the next one is transformation tuning, which is similar to head tuning, but you have some transformation matrix in the bottom of head and tune it. And all the other parameters are frozen. So this is methodology. And actually, I should mention that there are way more methodologies for different setups in the paper. So I had to skip due to time limit, but I recommend to take a look. I'll move on the result very quick as the time is limited. So we experimented with a range of classification data sets like sentiment analysis and so on. And the number of classes vary from 2 and 13. We used GPT-2 and 16 training examples. And we relaxed the assumption of perfect balance in the training data, which is a more realistic setting. And we run 80 different times because these models are known to have high variance. So we wanted to see the average case and worst case. So here are results, and there are many numbers, but we can see one by one. So first, let's look at prompt tuning results and compare direct models and channel models. And we see that channel models are much better across all data sets. And we find that this is because channel models have much lower variance and higher worst case accuracy. If you look at best case accuracy, direct models are often better, but their worst case accuracy is so terrible, so that on average, channel model is better. We find that head tuning is a surprisingly powerful baseline, being the best direct baseline. However, channel prompt tuning still outperforms all the direct baselines, especially on datasets like Yahoo and Wikipedia, where the number of classes is the largest. And we have some interesting observations here. So we look at, we vary the number of training data to see the impact of data size, and we see channel models are more competitive when there is smaller number of training samples, but it is less competitive when the training samples increases. So this is really a consistent result from intuition from previous work. For example, et al. Provided theoretical analysis that channel models are more competitive in the low data region. And we also did ablation to see the impact of imbalance in training data. And what we see here is when the data is significantly imbalanced, all the direct models don't really work, but channel models are relatively stable and achieve much better performance when the data is imbalanced. And it's also worth to note that when data is perfectly balanced, direct model could be better. I'll kind of skip this slide just as a matter of time, and I'll give a quick summary. So we saw that prompt-based learning has shown great potential, but it has very high variance. So we propose to tackle this problem by introducing a noisy channel model. And we find that this model works much better in terms of variance and worst case accuracy. Our observations show that channel models are more preferred, especially when K is small, training data is imbalanced, number of classes is large, and generalization capacity is required. However, we have very strict limitation, which is we only focus on classification. So future work should investigate more on how to extend this beyond classification. And all in all, I think this is a really exciting topic. It's an emerging topic that just started to be studied in like less than a year ago. So there is not a lot of work to be done. Okay, now I will maybe quickly move on to conclusion. So just as a summary, we saw impressive progress in NLU, but they have been developed with many unrealistic assumptions in models, tasks, and learning methods. And in today's talk, I argued that we should relax these assumptions one by one. So we first saw how we can retrieve the knowledge from Wikipedia and push the QA performance from 26 to 83 and extend it to a wider range of tasks. We then relaxed the assumption of well-defined user input by introducing a new task called Ambiguity that embraces potential ambiguity in user questions. And we set the baseline level for the task. Finally, I discussed language model prompting that learns a new task from a handful of training examples with little task-specific parameters. And in particular, we suggested that channel models could be a solution to solve the variance problem. And of course, I cover a subset of interesting topics, and there is a lot of work to be done for real-world NLU. And I strongly believe that the advances should be made in every possible dimension, like new tasks, new models, and new learning methods. And the balance is very important. So yeah, I hope you find it interesting too. I'll just skip the future work. And finally, I'd like to mention my collaborators, whom I was very fortunate to work with in the past few years. And yeah, that's it. And thank you for listening. And now I will take some questions.